want to test hypothesis testing about a population proportion. So this is 10.2. Hypothesis testing about P. P being population proportion. Okay, so what is the idea here? In general, before we even look at the handout and identify two very important statements here, and we go through our first example, what is the idea behind testing, hypothesis testing about anything? We're going to discuss in 10.2 population proportion and the population mean in the next section, 10.3. That's it in chapter 10. So what is the idea? We're going to, of course, have a claim. In number 2, we're going to select a sample. As we know, legitimate, etc., etc. In number 3, we're going to determine what is called, I like to call it, Z statistic. Your book, of course, calls it Z sub 0, which is legitimate as well. That's okay. It's a good notation. So this calculation will be our p hat minus the mu of p hat. This we know from a previous chapter, over the square root of p sub 0, 1 minus p sub 0 divided by n. Again, this is not news because this is the distribution. This is the distribution of p. So we're going to determine this. So we're going to say that the distribution of p hat is approximately normal. Of course, we're going to test the conditions. I should have said that as number sample in number 3. Test conditions. We always do that. What conditions? You remember from the previous chapter, conditions of independence and normality. These have to be tested before we continue. Okay, but we know that p hat is approximately normal with mu of p hat, sigma of p hat, where sigma of p hat is this. Okay, in number 4, after we complete that, so we have a claim, we take the sample, select the sample, we test immediately, we test the conditions, we create what is called Z statistic. This is a number coming from the sample. How? Like this. What do I do next? Well, we do know, we select from the very beginning what alpha is. Alpha could be 0.05. Alpha could be 0.01. I don't know. This is our decision. We are researching, so this is our decision. It will be given in the problem. Given each problem. Okay, in number 5, depending on, there are two possibilities. Because it depends on the null hypothesis and the alternative. So with a claim, we already know that we will have, once we have the claim, we have the null hypothesis and the alternative hypothesis. That's what I have. Once I have the claim, I have those two. Then I collect the sample, I test the conditions, I determine the number or the Z statistic coming from the sample, because this is normal or maybe not. We also have conditions in which it is not, or the conditions are not fulfilled. The conditions are not fulfilled, I cannot assume normality. Okay, then we have our level of significance, alpha. It's our decision or the researcher's decision, or is given in each problem. And then we have two possibilities, a two-tailed test and a one-tailed test. Where does this come from? From here. If this has equal and this not equal, it's a two-tailed test. If this has equal and this greater than, it's a one-tailed test. If this has equal and this has less than, it's a one-tailed test. So if it is a one-tailed test, if it is a two-tailed test, then we will divide alpha, like we always did, in 2 equal parts. If it's a one-tailed test, we will not divide alpha in 2 equal parts. If it's to the right, then I will have it here. So this is the alpha. This is alpha over 2. This is alpha over 2. Here I have the entire alpha. If it's the other side, then it's the other side. I will have alpha here. These are the 2 possibilities for one-tailed test, and this is the only possibility for a two-tailed test. Okay, finally, now the conclusion. If this number, whatever I get here, if this number falls in this area, or falls in this area, or falls in this area, I fail to reject. Fail to reject. Fail to reject. Fail to reject. However, if this number, after I calculated, it's coming from the sample, if that number falls here, or inside here, in this territory, or here, in this territory, if that number is a number somewhere here, or somewhere here, or somewhere here, I will reject H naught. Reject. This is the rejection area. This is the rejection area. Reject. Reject. And what will I say? I will say there is sufficient evidence to reject, coming from the sample, to reject the null hypothesis. What will I say here? There is insufficient evidence to reject. I fail to reject. There is insufficient evidence. So the sample does not support the alternative. It still supports what I knew from the past. This is the theory behind hypothesis testing. Any questions? You will see how this works the entire day today. But any questions right off the bat? Anything? Okay, so let's see how this works. Now, what I wrote here for you, we say that the results are statistically significant when the observed results coming from the sample are unlikely under the assumption that the null hypothesis is true, and we reject. What does that mean? This answer, if it falls here or here, is unlikely. So I have to reject. It wasn't expected. It fell in the tails. So I have to reject. It's significant. We say statistically significant. That's the wording. So the data coming from the sample is really giving us the information that is statistically significant. It's in the tails. It's unlikely. So then we have to reject the null hypothesis. I have not talked about the p-value yet. I will. I'll come back and talk about the p-value. Right now, this is the structure. And we're going to look at StatCrunch as well as the graphing calculator. Okay, any questions right now? This is the exact same procedure for mu. Exactly the same procedure. Okay, so let me put this away for now. And let's start with our first example. A simple random sample, an SRS, of 1,000 people, n equals 1,000, finds that 534 are in favor of banning cell phones while driving. Does this suggest that more than 50% of the people favor this policy, or we just obtained the result by chance? Will it be unusual to obtain a sample proportion of 0.3, 0.534 or higher from a population whose proportion is this? A lot of questions here, kind of confusing for a moment. Let's think about it. I have the number of people who said yes out of 1,000. I can immediately determine p hat. So p hat is 534 divided by 1,000. That's what the problem is saying, about 0.534. So then when I read carefully, it says, does this suggest the more than 50% of the people? So this is clearly telling me that the null hypothesis is that P equals P0. P0 equals 0.5. That's what it says, 50%. So I'll change it, of course, because I have to put the number, or I can put it here. The alternative, or H1, says, does this suggest that more than 50%, which means P greater than 0.50? From here, I immediately identify the fact that this is a right-tailed test. It's a right-tailed test. Okay. How do I conduct the test? I have the claim, I have the null hypothesis, I have the claim. I already have the sample. I collected the sample, 1,000 people, 534 said yes, I determined the proportion. And now I have to determine this z statistic. And here is how I determine it. So I have z statistic equals p hat 0.534 minus the mean. Before that, sorry, let's identify the distribution of p hat, so you know where all these pieces come from. So this is right. I'm rushing, and I don't have to. Sorry, we have to test the conditions. Test conditions. Test conditions first. The conditions are that n p0, 1 minus p0, has to be greater than or equal to 10. This is the condition for normality, which we always have to do. N, 1,000, multiplied by p0, 0.5. 1 minus 0.5. So let's see how much this is. 1,000 multiplied by 0.5, multiplied by 0.5. I got 250, definitely enough. So this is first condition. Second condition, it was that n is less than or equal to 0.05 times the population. So the population is the entire US. I didn't write that, but it's the entire US. So this is definitely 1,000 is definitely less than 0.05 times 360 million. No question about that. So this is the condition of independence. Both conditions are fulfilled. Now I can conclude, I'm going to erase it from there, it has to be here. So I can conclude that p hat is normal, or approximately normal, with a mean. The mean of p hat is 0.5, sorry, 0.5. And this is the sigma for p hat. We can calculate it. So sigma for p hat is the square root of 0.5 times 1 minus 0.5 divided by 1,000. Let's see how much this is. We're going to do this much faster with StatCrunch and much faster with the graphing calculator, but we have to go through the steps just to understand what's happening. So I have the square root. The top is 0.5 squared, and I divide by 1,000. Close the parenthesis, and I get 0.015 0.0158. So this is 0.0158. Okay. Step 1, check the conditions of independence and normality. Done. Find the distribution of p hat. Done. Calculate z statistic, also called z sub naught or z0. Fine. We are ready now. I'm going to erase them from here. They don't belong here. I was rushing. I have to do it step by step. And we have to check everything. This does not belong here. Has to wait. Sorry about that. Moving on. Now we determine the z statistic. Z statistic, that I like to call it, or z sub 0, that's fine too. Both are perfect. Will be p hat minus the mu of p hat divided by sigma of p hat. We have everything. We have p hat, 0.534. We have mu right here, 0.5. We have sigma right here, 0.0158, and I calculate. And so this is 0.034 because 0.534 minus 0.5 will be 0.034. And I divide by the previous answer. I'm lazy to put it in. It's right there. Oh, I didn't mean that. I meant 0.034 divided by the previous answer, please. Yes. Okay. Oh, these calculators, 0.34. You have to be very careful. For some reason, sometimes when I turn this on, this has never happened to me with the old calculator, ever. When you turn it on, you have to wait for a second for it to wake up. With the previous ones, I never had that problem. Divided by the previous answer, yes, 0.034 divided by the previous answer, and I got 2.15. Now, I am not going to calculate the p-value just yet. I want to determine, show you the graph, and then we're going to calculate. I'll explain what the p-value means, and I'll draw the conclusions, and then we will check the conclusion with the 95. Okay. At this point, this problem does not give the level of confidence. Let's choose 0.05, level of confidence. Okay. We already know that this is a right tail test. Agreed?